Welcome. The first part of this course deals with differential calculus. The central concept of differential calculus is that of the derivative of a function. However, we will start by studying the concept of limits, which we actually ignore much of the time. So, what is the derivative? Why is it important? And why bother with limits if we are going to ignore them much of the time? The last question first. We need limits to define the derivative in a mathematically acceptable way. That requires a fundamentally new process, one that's not purely algebraic. Turning to the first two questions. The derivative has several different interpretations or motivations. The most important for applications is that it captures the idea of rate of change in general. One of the most familiar examples of a rate is that of speed. If you are moving at a steady pace, think of marching to the steady beat of a drum, or driving on a flat, straight highway with cruise control on. Speed is distance covered per unit time, or more generally, distance covered divided by time taken. You can do this calculation over any time interval and always get the same answer. This is essentially the fact from high school algebra that rise over run is same for any 2 points on a straight line. But what if you are speeding up or slowing down, or maybe both? When you are driving in stop-and-go traffic, what is the speedometer really measuring? This is the problem Isaac Newton faced when he started studying motion mathematically. He came up with the concept of derivative to deal with this issue. Let's take a simple example. An object freely falling under the force of gravity and air resistance is neglected. Galileo had already determined that the distance traveled is a quadratic function of time. Let's look at distance over time in this case. Imagine dropping a cannonball from the top of a tower. This is just a thought experiment. No creature will be harmed by an actual cannonball. And that ruler is painted on a wall of the tower starting at the top. 3 seconds after the ball is dropped, the ball is at the spot marked by 16 times t squared feet. At t equals 1 second, the ball is at 16 times 1 squared equals 16 foot mark. At t equals 2 seconds, the ball is at 16 times 2 squared equals 64 foot mark. At t equals 3 seconds, the ball is at 16 times 3 squared equals 144 foot mark. At t equals 4 seconds, the ball is at 16 times 4 squared equals 256 foot mark. In the 1 second from t equals 2 to t equals 3, the ball falls from 64 foot mark to the 144 foot mark, a distance of 80 feet. This gives a speed of 80 feet per second. In the 1 second from t equals 3 to t equals 4, the ball falls from the 144 foot mark to the 256 foot mark, a distance of 112 feet. This gives a speed of 112 feet per second. Distance per unit time varies. We get different answers for different intervals. Newton's idea was to focus on a particular moment and find distance divided by time for shorter and shorter intervals of time covering that moment. Let's fix the moment t equals 3 and find the speed over shorter time intervals. Let's take the time interval from t equals 3 to t equals 3.1. At time t equals 3.1, the object is at 16 times 3.1 squared, that is 153.76 foot mark. The distance covered from t equals 3 to t equals 3.1 is 153.76 minus 144, which is 9.76 feet. The speed is 9.76 divided by 0.1 equals 97.6 feet per second. What about t equals 2.9 to t equals 3? At time t equals 2.9, that object is at 16 times 2.9 squared, or 134.56 feet mark. The distance covered between t equals 2.9 and t equals 3 is 144 minus 134.56, or 9.44 feet. The speed is 9.44 divided by 0.1, which is 94.4 feet per second. The two values for speed, 97.6 feet per second and 94.4 feet per second, are not that different. What happens if we take even shorter intervals? Let's do this algebraically to make our calculations more efficient. Between time 3 and time t, the object covers a distance of 16 t squared minus 144 feet. The time interval is t minus 3 seconds. So the speed during the time interval from 3 to t is 16 t squared minus 144 divided by t minus 3 feet per second. If t is less than 3, we might calculate the speed as 144 minus 16 t squared over 3 minus t, subtracting the smaller value from the larger. That's same as what we had before, because the numerator and the denominator are both multiplied by -1. Now let's tabulate the speeds for the interval between 3 and the listed value of t. Let's put in the values we found before. Speed of 80 feet per second for t equals 2, 112 for t equals 4, 97.6 for t equals 3.1, 94.4 for t equals 2.9. Plug in the value of t in the expression above in line 4, that is 16 t squared minus 144 over t minus 3, to get the corresponding value of distance divided by time, and enter in the table. So continuing the table, 96.16 for 3.01, 95.84 for 2.99, 96.016 for 3.001, 95.984 for 2.999, 96.0016 for 3.0001, 95.9984 for 2.9999. When we look at the values in the table, we see that the values for the speed are getting closer and closer to 96 feet per second. As the values of t get closer and closer to 3. It looks like when t equals 3, the speed should be 96 feet per second.